Okay, welcome to our next installment of the California Dreams Technical Seminar. I'm Steve Crago, the Director of California Dreams. I am glad to be back live on our technical seminar series after missing a few weeks while traveling. One of my recent trips was to Santa Barbara, where I was glad to see our friend Mark Rodwell, who is today's speaker. Dr. Rodwell received his Ph.D. from Stanford University and is currently the Doluca Family Endowed Chair in Electrical and Computer Engineering at UC Santa Barbara. He was recently the director of an SRC DARPA Wireless Research Center and has done lots of interesting work in high-frequency transistors, ICs, communication systems, and is the winner of many prestigious awards. We're glad to have Professor Rodwell with us, and he's going to tell us interesting things about device physics today. So Mark, please take it away.
Well, thank you so much for the audience. I'm really glad and honored to be speaking to all of you. I would like to start by acknowledging not only my present PhD students, but all of my past PhD students, and in particular, my friends, collaborators, and in some cases, past PhD students at Teledyne Scientific Center, Bobby, Zach, Logan in particular. Oh, and Miguel, goodness, greatest of all, Miguel. Okay, so let's get started and talking about the role of indium phosphide technologies in high-frequency electronics. Okay, first let's talk about the applications. I'll go through these very quickly. Why would we want to build electronics at very high frequencies? Well, let's just flash through for you a number of quick examples. Maybe I want to do wireless backhaul for future high-density wireless communications. I can build a wireless communication systems on a 250 gigahertz carrier, provide a terabits per second of capacity over 1.5 kilometers, even using sensible safety margins and even doing it when it's raining real hard, 50 millimeters per hour. And I'll do that with 2 polarizations and with MIMOs that I've got 8 total channels, 125 gigabits per second, 1 terabit per second total. And the baseline for the MIMO array is a very compact 1 meter. There's been recent discussions. I'm a little bit concerned about some of the practicality of this, of moving data around data centers where we're doing AI using wireless links. We would use a couple of bands, one between 75 and 165 gigahertz, the second between 195 and 305 gigahertz. We'll do that using 16 QAM, 2 polarizations. When you plug all of those numbers together for that pair of antennas with the 2 polarizations, that's 1.6 terabits per second. Won't use phased arrays for that, just use highly directional horn antennas. Easy to get 100 meters range. The challenges there are, can we get down to the necessary 1 picojoule per bit or less? There's a bit of concern about someone putting their hand in the way or getting crosstalk between beams, and that would be a longer discussion for a different venue, but maybe in the questions. Another application also related to that is the current standard for optical links in those data centers that everybody's working towards is 800 gigabits per lane. The next presumably is 400 gigabits per lane. The next is presumably going to be 800 gigabit per lane, which if you use PAM4 signaling is going to require an analog bandwidth of about DC to 250 gigahertz. I don't really know if we can build an optical modulator with that bandwidth, but half that bandwidth has already been done. And if we're going to do that, we're going to need very, very fast electronics to do that in both the transmitter and the receiver. And the indium phosphide technology, even today, can handle those kind of bandwidths and voltages. So that's exciting. Perhaps in an application that might either be civilian or military, we want to build a high-performance imaging radar for something like driving on the ground in inclement conditions. And there's an architecture called a Mills crossed array radar, which allows you to build an image with n squared pixels in it with 2 arrays that are each only n by 1, gives you more image pixels with simple hardware at some cost and signal to noise ratio. And when you do a link budget for that, again, very conservatively with good operating margins, and with today's sort of hardware performance, you could do this at 200 meters range in heavy fog and still see a soccer ball. And 200 meters range is about 10 seconds warning at freeway speeds. So that looks pretty interesting. How about synthetic aperture radar? Over 10 years ago, DARPA had a program called VISAR that was video rate synthetic aperture radar. And the idea was to build a system that gave you the resolution and range of an infrared system, but could see through clouds and fog. And that system had a 50-watt vacuum tube. Well, today we can produce that 50 watts by using a phased array with indium phosphide, 16 by 16 subarray at 100 milliwatts per element, 2 tiles, you're at 50 watts. So we could replicate that system with a solid state source. And I need to be a little bit vague about this, but there are interests within the defense community about building a space-based synthetic aperture radar system. And the advantage there is at higher frequencies for a given link budget, the aperture area is smaller, and that's a big deal if you're going to put things in orbit. If we could look at a phased array radar at the very high frequencies, the reason for doing a phased array radar at very high frequencies is you can get a very tight angular resolution, even from a small aperture. In this case, I'll make the array 3 by 3 inches, 3.5 by 3.5 inches, which is 128 by 128 elements. That gives us a bit less than a degree of beam width. What can that do for you? The resolution at the image plane is about 16 meters, but you can detect something as small as a baseball at a kilometer range if the weather is good, or cut that down to about 400 meters range if it's raining crazy hard. So again, that might be very interesting. It gets a bit more of a stretch because of atmospheric attenuation, but you could talk about space-based or air-based radio communication systems at these very high frequencies. What happens is as you get close to the ground under inclement weather conditions, the ranges can get pushed down to the range of 3 kilometers if you're trying to do 5 gigabits per second. And that's really not very good if you're talking about an airborne system. But if you get above the clouds, then the range becomes more interesting. So perhaps that's an application, though the argument for pushing up in carrier frequencies is weaker in this case. Okay, so with those as a set of motivations for why to build fast electronics, let's talk about first where we are in terms of the state of the art in high frequency transistors. And here I'm showing you excellent work funded by DARPA at Northrop Grumman and Teledyne, and with the Teledyne team, considerable interaction and collaboration contribution by my team back in the day. The HEMPs from Northrop Grumman have about 1.5 terahertz power gain cutoff frequencies. They've built amplifiers to about 1 terahertz. The HBTs at the 130 nanometer node have about 1.1 terahertz, fmax with about 3 volt breakdown, and they've built circuits up to about 670 gigahertz in this. If you drop from the 130 to the 250 nanometer node that's a bit cheaper, the bandwidth drops, but you get a bit more voltage. And this is quite a nice technology for building power amplifiers in the 100 to 200 gigahertz frequency range. Just to give you a sense of hero results with those technologies, we've built digital circuits up to flip-flops up to a little over 200 gigahertz, oscillators above 650 gigahertz, amplifiers that I'd mentioned above 650 gigahertz, and transmitters and the receivers in the 550 to 600 gigahertz range. So it's really important to understand that these are hero experiments. The receiver's not very sensitive and the transmitter has very low output power. So this is sort of a hero experiment to show that you can do this. And for real performance, you need to drop down in frequencies. So let's drop down in frequencies to where real things can be done at 100 to 300 gigahertz. And here I'm showing you a lot of density information at once. I'm showing you a summary of IC performance in the 100 to 300 gigahertz range. First, you see noise figure as a function of frequency. The gold dots are gallium nitride. Gallium nitride, the black dots are CMOS, the red dots are silicon germanium, and there's noise as a function of frequency. And what you see is that the winners are the indium phosphide field effect transistors, but second place is the indium phosphide bipolar transistor. If you look at the power amplifiers as a function of frequency moving in narrow frequency chunks up all the way to 330 gigahertz, graphing power added efficiency in the vertical axis, log scale, output power log scale on the horizontal axis, what you see again is that the indium phosphide HBT is the clear winner in terms of output power and efficiency in all of these frequency bands, with a bunch of dramatic new results from the ELGAR program with published efficiencies up to 25% at 50 milliwatts at 220 gigahertz, and much better results before long. And there's a real feasibility, as I'll mention in a second, to get substantial increases, dramatic increases in efficiency in these higher frequency bands as well. Let's just look at a couple of results here. There's Miguel's 1.1 terahertz HBT. Here's a bipolar transistor LNA with about 5.75 dB noise figure at 215 gigahertz. In the 250 nanometer technology, here's about a half-watt power amplifier at 150 gigahertz. There's that record Zach Griffith power amp at 25% efficiency at 220 gigahertz. So there's a lot can be done with this technology, and it's really driving the high-frequency systems forwards. To give you a sense of what could be done in Elgar Phase 2, Teledyne, UCSB are working hard. Here are some simulations from my group. We've taken the raw transistor cell, simulated its efficiency at 3 frequencies, 150, 225, and 280 gigahertz. And then we've got a full IC design that will soon be fabricated by Miguel and his team at 220 gigahertz. Well, the transistor simulates at 35%. The power amp simulates at almost 30% at 220 gigahertz. But look, the same transistor simulates at almost the same efficiency at 280 gigahertz. So we think that it's quite feasible that we'll see up to 27% efficiency at roughly 100 milliwatts at 280 gigahertz. So again, that would put us with points sort of about here in the power frequency plane. So again, major advantages are possible. Is this a toy technology or is it a high volume technology? Well, it's not silicon CMOS, but in comparing this, for example, to silicon germanium, which silicon germanium technology? The slow ones that are in high volume production or the faster ones that are not? I can't really give you all the data on that. I don't have it, but I'll comment, for example, this power amplifier has 217 transistors in it, all told. And they're yielding at something like 75, 80%. And that's easily sufficient to realize circuits like this monolithic transmitter and receiver at 280 gigahertz. Okay, let's just move on and let's talk for a moment about circuit design just for a second. Even with such fast transistors, and certainly with somewhat slower ones, if you're working in the 100 to 300 gigahertz range, your ratio of power gain cutoff frequency to signal frequency is kind of low. So you don't get a lot of gain out of the transistor. And so if you go to the conferences, there are very large numbers of papers publishing various tricks to improve the gain per stage. And it's really important to understand that no one actually cares about gain per stage except for bragging rights. What you care about is receiver noise figure and transmitter output power and efficiency. And it's fundamental theorems that you could prove rigorously that all of these tricks help you not at all in improving the things that you care about the most, which is the cascaded noise figure, meaning the gain of the first stage plus the gain of the second stage divided by the noise of the first stage, excuse me, plus the noise of the second stage divided by the gain of the first stage, and so on. That is not improved with these circuit tricks. And the same is true of a graph of power added efficiency versus output power. So those two parameters are fundamental properties of the transistor itself, just like FT and fmax are. And it's the goal of the circuit design to get as close as you can to those fundamental transistor limits. Okay, how do we make faster bipolar transistors? What do we need to do? The first question is why? And there are a couple of reasons, but before, let's just look at some data. Again, looking in the Teledyne technology, they're at the 250 or the 130 nanometer node with either 650 gigahertz or 1.1 terahertz fmax. What's the implication for a power amplifier? Well, at 220 gigahertz, the implication is going from 18% to 25%. So the higher fmax helps you. For a low noise amplifier, the implication is going from 7.2 dB to 5.5 dB noise figure. So if we produce faster yet transistors at these frequencies, that will give us lower noise in our low noise amplifiers and more efficiency in our power amplifiers, or we can use the transistors to work at higher frequencies. What do we need to do to build ultra high frequencies? Before getting into the details, let's just look at the basic points. Here I'm considering two spheres. One is Jupiter, the other is a golf ball. They're definitely not the same size. Volume varies as the cube of radius, surface area varies as the square of radius. So as you make things smaller, the surfaces become more and more important. And in semiconductor devices, your two kinds of surfaces are metal to semiconductor interfaces, in other words, ohmic contacts, and dielectric to semiconductor interfaces, aka gate dielectrics. So as we go to terahertz transistors, we need very low resistivity contacts. We need very, very thin gate dielectrics. Focusing a bit on the ohmic contacts, I'm giving you numbers here for the upcoming next technology node for the indium phosphide HBT. What we need is extremely low contact resistivity, 1 ohm in a square micron, or 10 to the minus 8 ohm centimeter squared. We need the penetration depth of the contact into the semiconductor to be less than a nanometer. And all of that has to be done on a contact that is carrying as much as 50 milliamps per square micron. In other words, 5 million amps per square centimeter. So these contacts have also got to be as hard as nails. Your other two issues are with those crazy high current densities, you've got to worry about a lot about thermal design of the transistor itself and thermal design of the integrated circuit. And the final point is you need to have enough quantum states to carry the current. As you make your device smaller and smaller, the electron wave function has fewer energy levels available, and so there's less places to put in an electron, and so there's less ways to carry current, and you must deal with that. So let's do some very basic things, but it's important. We can have depletion layers. Everybody knows that a depletion layer has a capacitance of epsilon A over D. Everybody knows in moving an electron through a depletion layer that you've got a transit time that's basically the thickness divided by the velocity to within some constant. It's just as simple, but surprisingly fewer people know that a depletion layer has a maximum current density. And the reason is electrons have charge, and charge screens field. So if you put enough electrons into a depletion layer, the field collapses and they slow down. So the maximum current per unit area varies in proportion to the inverse square of the thickness of the depletion layer. That's a critical important point. In terms of resistances, everybody knows about bolt resistivity, rho times L over A. Everybody knows about contact resistance, resistance per unit area divided by area. Very often ohmic contacts, the current is flowing horizontally through the contact, through the semiconductor, and then vertically through the contact. There's a very complicated hyperbolic cotangent formula there, but trust me, if you go through the math, it's an excellent approximation to say that the resistance is the contact resistance per unit area divided by the area of the contact, plus another term I won't waste time on involving the semiconductor layer. Now, in terms of capacitances, everybody knows about epsilon A over D again, but fringing capacitances between a pair of conductors like this is a critical consideration in the scaling of high-frequency transistors. And similarly, the fringing capacitance gives us the irreducibility of interconnect capacitance in VLSI, setting a minimum power dissipation there. Other key things we need to think about are thermal resistance. We have a thermal resistance of a long skinny stripe that varies basically as 1 over its length, with a logarithmic term involving the ratio of length to width, and the thermal resistance of an oval chip, which if it's square varies as 1 over the width of the chip. And then, as I mentioned, the available quantum states to carry current. So let's spend a little bit more time on that. Here I'm showing you a plot in 1 dimension, but you can easily imagine it in 2 or 3 dimensions of energy versus k vector, wave vector, or momentum in some semiconductor. If we want to know the charge within the region, we need to count up, in other words, integrate all of the quantum states that are occupied between the band edge and the Fermi level. That's easy. If we want to know the current, assuming that only the right states are populated and not the left, what we do is add up the charge times the velocity of each state, and that's just another simple integral. And all of that, the rest is just math. This leads to simply what we call ballistic transport theory. That's got some fun implications of that. In the ballistic limit, a field effect transistor, rather than having the classic mu C ox over LG VGS minus V threshold squared equation, has current that's limited by this quantum state density, and it varies as VGS take away V threshold to the 3/2 power. Within those field effect transistors, we have what's called the state density capacitance, which is the variation of charge in the channel with voltage on the channel. And that has a capacitance-like effect, and it's proportional, that capacitance, to the effective mass of the semiconductor. What I find really fun, and I'll mention this in a moment in more detail, is that the IV relationships of a bipolar transistor no longer are e to the QV over KT, but look somewhat different with a quadratic variation with bias. And another thing that's really, really critical for doing exactly the same calculations is even if the tunneling probability through an ohmic contact is 100%, you still have a non-zero resistivity to your contact. And at least in the case of a bulk metal contacting a bulk semiconductor, that resistance varies as the inverse 2/3 power of the doping. So these are key limits to understand. Just one thing I want to spend a little bit more time on, I'm not sure it's important, but it sure is fun, is we all have learned in school that I equals IS e to the QV over KT for a bipolar transistor. But that's assuming that the Fermi level in the emitter is below that of the base or of the barrier. And if you push up the bias enough, and we do in modern transistors, the Boltzmann statistics that you were assuming to get that exponential IV characteristics no longer hold, and the curve starts to flatten out with a Fermi-Dirac integral. And this dot is where we are presently with today's technology. And you can see the slope of the red line is significantly slower, less steep than the slope of the black line, which is our usual assumption. So even today, this is reducing the transconductance of indium phosphide HBTs. And the next scaling generation is going to be further up the line. So this is a definite consideration. So here's how we play the game for scaling. We have a transistor, and we want to replace it with a new transistor such that no matter what circuit we put it in, the circuit runs twice as fast. And if we do that, we need the same voltage, the same currents, the same resistances, but half the capacitances and half the transit times. What do? We look at the transit time in the base, we look at the transit time in the collector, we look at the collector base capacitance, we look at the maximum current, and so on. If I want half the base transit time, I need the base to be square root of 2 times thinner. If I want half the collector transit time, I need the collector half as thinner. I want half the collector base capacitance, but the layer got twice as thin, so the area needs to be 4 times smaller. I look at the maximum current, the area is 4 times smaller, the capacitance is, the thickness is 2 to 1 smaller, so phew, the current stays the same, which is what I want. I look at the temperature, and that involves the power dissipation per unit length and a logarithmic variation, which is pretty slow, involving the length to width ratio. So the message there, I need to keep the power per unit length constant. So I need to reduce the area by a factor of 4 while keeping the length the same. So that means that the width needs to be reduced by a factor of 4. I might need my resistances to stay the same, even though I've got 4 times smaller area. So I need the resistance per unit area of the ohmic contacts to be 4 to 1 smaller. Isn't that amazing? I went through and we derived together scaling laws for bipolar transistors in about 30 seconds. Okay, it's really that simple. If we want to double the bandwidth, we need the lithographic widths of the emitter and collector junctions to be 4 times skinnier. We need the current density per unit area to get 4 times bigger. We need the current per unit emitter stripe length to be the same. Semiconductor layers get thinner. Contact resistivities need to get 4 to 1 better. Narrow junctions, thin layers, extremely high current densities, and above all, ultra low resistivity ohmic contacts. Just as a comment, because people ask what's happening to the breakdown layer. Gee, you doubled the bandwidth, your semiconductor layer gets twice as thin, so you get half the breakdown voltage. And I'll just comment quickly that we're getting close to the limit where that's really not true at all, because breakdown is never less than the band gap. The impact ionization breakdown is never less than the collector semiconductor layer band gap. The tunneling breakdown is never less than the base band gap. And so with these two, as we approach these limits, breakdown starts to slow down and it decreases with scale the device. And this is the way this is the only reason all high frequency transistors work, whether indium phosphide or even VLSI CMOS. So as I mentioned, the critical challenge in terahertz bipolar transistors is ultra low resistivity contacts. And here I'm showing you plots as a function of doping the contact resistivity to N InGas, to N indium arsenide, and to P InGas. Our emitters are generally to N indium arsenide, to our base contacts are to P InGas. The red dots are experimental data, mostly from my group. The black line curves are theoretical calculations, including tunneling through the barrier. The bottom black line is that quantum state density limit that I mentioned to you. It's fun to note that the experimental contact resistivities are within a factor of 10 of the quantum limits. The key thing that I would draw to your attention is we have demonstrated contacts good enough for the 32 nanometer node, which would give us about a 2.5 terahertz fmax. So why don't we have those 2.5 terahertz transistors today? And the answer is reproducing these contacts, particularly the base contact, within a full HBT process flow. Just showing you results from 2015. Here's an indium phosphide HBT built by my group. Power gain cutoff frequency is about 2 terahertz. What I really want to draw to your attention is that the overall base is 14 nanometers thick, but the base contact has sunk 2.7 nanometers through that. And you say, oh, gee, that's not that big a fraction, but it's much worse than you think. And this is going to be a limit to how far we can push this. So there are a couple of key challenges in doing the next technology node, 64 nanometers, that would bring us to about 1.8 terahertz. The first one I'll mention just briefly is RC parasitics along the length of the transistor, both the fact that you've got in base metal resistance, kind of like gate resistance and a FET, and that becomes worse as we make the stripes of the transistor skinnier. So we deal with that by making the stripe shorter, and then the problem is we get killed by the end capacitances. So this is a university-like solution to the problem. A production-level solution would be different. But even at the 130 nanometer nodes, what we did to reduce that resistance is produce a significant undercut in the semiconductor under the base metal, and to make the base metal thicker and make a larger fraction of it gold rather than a mix of other metals. In terms of the pad, you're looking at a cross-section along the length of the transistor, sort of before and after. And we worked, again, crazy university tricks in producing a deeper undercut under the base post so as to get less end capacitance. And we also worked to lose less length of the end of the emitter through chemical undercutting. Okay. The other question, the key challenge, the thing that's more fundamentally important, is obtaining good base contacts. And here I need to really draw your attention to this point here, is although the base is about 15 nanometer thick, there's only the top 6 nanometers of that is doped at the super heavy levels that are required for super good contact resistance. Well, why would that be? Okay. And the reason is because the base doping causes Auger recombination, with the rate of recombination increasing as the square of the base doping. So if I dope the base heavily enough to get this wonderful contact resistance, and if I do it over the full thickness, I'll get a very, very poor DC current gain. So this is the challenge. We're building transistors, and we're already at the 130 nanometer node where the overall base is about 17 nanometers thick, but only the top 5 or 6 nanometers are super heavily doped. Already our base ohmic contact is sinking in about 3 nanometers. So the trouble is, why are we having that sink in that far? And the answer is to penetrate surface oxides that are getting there inevitably as part of the process flow. So what do we need to do for the next generation? And the answer is we need to break this conundrum by building a transistor that more closely resembles a silicon germanium heterojunction bipolar transistor. In other words, use a process flow like this. Build the base emitter junction, regrow more heavily doped material, then put the base contact on there, and then complete the transistor. And this does several good things for you. First of all, the base can be heavily doped here and lightly doped here, the heavy doping giving you nice low contact resistance, the lighter doping here giving you nice high DC current gain. The other advantage here is that the base is thin here for low transit time, but nice and thick here, giving you plenty of distance to have an ohmic contact that sinks in a little bit to push through that crap on the surface and give you a low contact resistivity. Presently, in our experiments that concluded about 4 or 5 years ago, we were doing this regrowth using gallium arsenide. We're pushing the doping up to about 10 to the 21st per cubic centimeters. So I should go back and just mention that in this regrowth, that we are doing this regrowth after forming the base emitter junction. So the emitter contact is a refractory metal, something that's hard as nails, can take the very high temperatures, and it's encapsulated during the regrowth with a silicon nitride sidewall, and not shown on this drawing is also a silicon dioxide cap on this. So here I'm showing you photographs of cross-sectional photographs of what these regrown transistors look like. You see the emitter here, you see the base regrowth here. It's a bit faceted, so you see a groove here. Here you can see it in cross-section with the semiconductor regrowth like that and the metal contacts. And so here's another contact here. Again, the regrowth is lattice mismatch, gallium arsenide, not InGaAs. Why? Because gallium arsenide you can dope more heavily with carbon without fighting difficulties with hydrogen passivation. And there's a lot of hydrogen floating around in MOCVD system. So we did get pretty decent results. These are transistors with emitters as narrow as 64 nanometers, the target dimensions with base regrowth. The DC current gains are not great, but they're okay. The Gummel characteristics, the common emitter characteristics look good. Getting extremely low resistivity contacts between the metal and the regrowth. The contact resistivity between the gas regrowth and the InGaAs original layer is a bit. Okay. So we're working on hydrogen passivation here to get the contact resistivities here. So this is work that's partially complete, but not fully complete. Okay, how do we build a faster field effect transistor? First, again, why would we want to do this? And I'm showing you here calculated graphs of noise figure as a function of frequency for different current gain cutoff frequencies for a field effect transistor using a modified form of the Fukui minimum noise figure expression. And what you see clearly is as the current gain cutoff frequency increases, the noise figure reduces. So we might want a higher cutoff frequency either to work at higher frequencies or to stay at the same frequencies and get a better noise figure for a more sensitive receiver. So how do we derive the scaling laws of these? It's sort of obvious that to reduce the transit time in the gate, to double the current gain cutoff frequency, we need to cut in half the gate length by a factor of 2. However, those fringing capacitances that I mentioned are still present between the gate and the source and the gate and the drain, and they're pretty much independent of the gate length. So you've got a parasitic capacitance here and a parasitic capacitance here that are independent of the gate length, and shrinking the gate length doesn't help you. So the only way to reduce the charging time of those is every time you double the bandwidth, you need to double the transconductance per unit width of your field effect transistor so that the GM to C ratio is cut in half. Sorry, it's doubled. Okay, now how do we do that and why is that not easy? And the answer here is, this is a bit heavy on physics. Let's hope that I can get through it easily. I'm showing you here a cross section and a band diagram of the gate to channel interface, gate metal, gate oxide, channel and barrier. So the first thing that you notice is the electrons, of course, have a wave function. So they're sitting not right at this interface here, but sort of distributed through the middle of the channel. The second thing to understand, as I'd mentioned earlier, is the channel is a quantum well. And to put more and more charge in it, we have to raise and lower the Fermi level. So changing charge requires change in Fermi level, which is simply voltage. And the ratio of charge to voltage is capacitance. So the channel has a capacitance that's associated with the quantum states within it. We have another capacitance that's associated with the fact that the electrons are not sitting here, but are spread through throughout the channel. And then we have the gate oxide. So transconductance per unit width is capacitance per area times electron velocity. If we wanted to double the transconductance, we need to double the capacitance per unit area. Okay, we'll use a thinner gate dielectric. Okay, we'll make the channel thinner. That will help us here and here. But the place that we're all stuck, and to date I have no solution for this, is I need also to double the capacitance per unit area of the semiconductor state density, and that involves changing the semiconductor material. So these are our FET scaling laws. These laws now broken. If we want to double the bandwidth, certainly we need to reduce the gate length. We need to reduce the contact resistivities, but we need thinner dielectrics, thinner channels, and that conundrum of somehow doubling the state density in the channel. So some of this we can do, not all of this we can do. The key things that we can do are everything but the state density. If we take a standard 3.5 field effect transistor that has a wide band gap insulator between the channel and the gate, and we replace that with a high K gate dielectric. Because the band offsets are larger here, we can afford to make this thinner, and that helps us double the capacitance per unit area of the gate dielectric. That's good. In addition, we can develop a process flow where the N+ regions sit directly on the channel instead of having a barrier between the channel, between the N+ layer and the channel, and that helps us with the contact resistance. The thing that the high K 3.5 FET process flow doesn't help us with is the channel state density. So in terms of the high K gate dielectric, although it didn't make it into VLSI because it didn't really meet all of the requirements, my group and a number of other groups nationwide 15, 20 years ago had developed high K processes for the 3.5s in an effort to build 3.5 MOSFETs. I'm just showing you this for a moment. Channel's about 2.5 nanometers thick. This is a high K ZR02 gate insulator, and we were building very, very good transistors with very good DC characteristics. So we've taken that technology and adopted it into a modern HEMT process flow with a gate dielectric replacing the wide bandgap insulator. I apologize, I don't have cross sections that show the intact transistor because the company that did the FIB managed to tear the sample apart in doing this. So you see the gate detached from the channel, but there's the channel. There is the high K gate dielectric, and there is the gate metal. And we managed to get pretty decent performance with transistors around about 25, 30 nanometer gate lengths. The power gain cutoff frequencies are about 1 terahertz, and the current gain cutoff frequency is about 500 gigahertz. I'd emphasize that these are not world record devices, but they're not bad. And we're hoping that Northrop Grumman might have some interest in bringing this process module in their technology that, along with the other things I've mentioned, might help them further improve their technology. Okay, so I've managed to sort of mostly stay within time. Next generation transistors for next generation systems. And here is sort of the California Dreams marketing slide. I've mentioned the applications, high-speed communications. Here I'm emphasizing the military applications because this is a government-funded centers. What can we do with this? We can get these technologies into Northrop Grumman and into Teledyne for the field effect transistors and for the bipolar transistors, push up the cutoff frequencies and serve these various systems applications that I've mentioned. So thank you so much for your time and attention. This would be a good time to take questions. Thank you.
Thank you very much, Mark. Who has a question?
I'll jump in. Hey, Mark.
Hey.
About the HBT scaling past 128 or past the 130, we always talk about thermal limiting your total performance. What do you see in the 64 nanometer proposed node in terms of like thermal resistance out of the collector?
So it's a great question. Here's the key number is the scaling laws keep the power per unit length constant, but as with each scaling generation, the emitter width is getting approximately 4 times narrower. So this would lead to a moderate, not a catastrophic increase in the junction temperature as you go through further scaling generations. So that's sort of the simple back of the envelope answer. Now, however, in the interest of brevity in this chaotic presentation, I'd comment that the scaling laws I've presented to you are themselves breaking in a favorable as opposed to an unfavorable way, because the emitter is getting skinnier faster than the collector is getting thinner. And so the current flow in the collector is no longer parallel plate. It's increasingly approaching a cylindrical scenario. And so that's also helping a little bit. Okay. A more serious question, sorry, not a more serious question is do we want to do balanced scaling? Do we want to have the next generation to have twice the FT and twice the fmax? Or do we want the fmax to double, but to allow the, square root of 2, excuse me. Or do we want the fmax to go up, but the FT to go up less rapidly because we want to keep breakdown voltage, right? And that kind of depends on the application. To the extent that we don't push up FT as fast as we push up fmax, the current density is going up less rapidly, and then again, that also helps with thermal. So it's a great answer, and it pushes us into places where these simple approximations are not necessarily giving us a clear answer. We need to be looking at it more carefully. Yeah.
Got it. Thank you.
Thanks, Andy. Yeah.
I have a question from the chat window, but I'm going to give a second for anybody else to raise their hand and ask a question live. Question in the chat window, and we can take more live questions after this, is thanks, Mark. Can you share your experience with the technology transition of Group 3.5 based HBT hemp devices, such as high-speed indium phosphate hemps from your lab to industry partners like Teledyne and Northrop Grumman? What were the key obstacles you faced during this transition?
So I haven't transferred any field effect transistor technologies to anyone, although I'd be eager if anyone wishes to take them. Usually the problem is you can't give away your ideas. But we have very successfully collaborated with Teledyne on many DARPA programs over the last 25 years. And I think that's really one of, I think that's the key answer is that the tech transfer was constant and ongoing throughout the research program, rather than us developing something at the end and then trying to find partners that were interested. We were partnered with Teledyne in a half dozen DARPA programs from as early as about the year 2000. And so we were developing process modules, Teledyne full process flows. In the early days, we were pace setting on transistor development and moving the full transistor across. As the process technology became more important, more complex, then the university could not keep up with Teledyne in terms of transistor development, but we were continuing to contribute process modules. And in this case, we're hoping to find DARPA or similar funding or CHIPS Act funding opportunities to help transfer the regrowth. So this is the model to do it, and I think Teledyne has been very, very successful. And of course, a key part of that is PhD students. I think I've had roughly 8 PhD students join Teledyne over the last 25 years. Some of them have since moved on, and some of them were circuit designers. But Miguel is key to that, and Logan Whitaker is in the hemp technology group at Teledyne presently. So those, I think, are the key messages.
Thank you, Mark. Ongoing collaborations are very important, and I hope one of the functions of our hub. Other questions?
So, Mark, your analysis has just been incredible. It goes beyond the key scaling considerations that you developed first, 15, 20 years ago, and now the limits are being set increasingly by fundamental quantum physics.
Yeah.
I wonder, are things going to become very difficult? You mentioned, for example, the current flow for the bipolar transistor is going to become relatively slower, increasing rather slowly with voltage, a quadratic form instead of exponential. Is that going to be a real problem?
Well, it sort of depends on, there are economic issues as well. Is if we were going gangbusters and we had armies of people, millions of people willing to buy this as a product, and we were planning the 64 nanometer node and the 32 nanometer node in the next couple of years, then I would say that, and assuming that you want FT to improve as well as fmax. If you don't want FT to improve, just fmax, you can leave the current density where it is. But with all those stipulations, this starts to be kind of a serious issue at the 32 nanometer node. However, so at some point you would actually start to want to go back to silicon with its higher state density, even though the electron velocities are lower. But before everybody says, Rodwell says we should do SiGe, that's the indium phosphide has a huge advantage today, and that's sort of as we pushing the transistor to the 3 or 4 terahertz sort of bandwidth. So what's limiting the bandwidth right now is the process technology. With each technology node is getting more complex and taking more capital investment. And the number of markets that is serving is not sufficient to generate the revenue to develop or to maintain those more complex processes. So, you know, the success of RF CMOS is you get these wonderful RFICs that are paid for by the computer industry, not the RF wireless industry. So someone else is paying the bills, right? So I'm sorry to bring you back to that. So yes, we would hit a fundamental, we would hit limits that would force us to think hard about our selection of materials. You know, somewhere around about 3 terahertz. But the 1 terahertz transistor was demonstrated in I'm forgetting, I want to get this right, so let me actually double check. The 1 terahertz device was demonstrated in 2011. That's 14 years ago. And the reason there's been slow progress since then is economics and market need, not physics. So, you know, that's the other thing that's going on here. Yeah. But I'm sort of hoping that with the explosion of data capacity because of AI and cloud computing, that produces some real major drivers for the high-speed business again. It's a great question, Peter. Thank you so much.
But along the lines of material choices as determined by quantum considerations, you also said that the density of states is a barrier for the field effect transistors. And do you see that other materials might provide an advantage?
Yes, and that's a great question. I think the key point to understand there is, unlike the bipolar transistor, where the density of states is sort of sitting as a problem 2 scaling generations away, the density of states is a challenge right now. I mean, it's significantly impairing the performance of even today's HEMPs. So I wrote many papers roughly 20 years ago trying to come up with crazy semiconductor physics solutions to that, but the growth and materials technology were all too complex. The 2 simple things that I do see as solutions specific for the RF wireless market is the carrier velocity also goes, you know, equals 1/2 mv squared. So if you increase the energy, excuse me, let me find the right plot here. If you increase the energy of electrons in the channel, the electrons are moving faster. And that gives you more current, even you've only got a fixed number of electrons. And so that's more VGS minus V threshold. So concisely, and I don't have the data to prove this, and it's hard to establish, but I believe the solution is 1, larger gate overdrive VGS minus V threshold. And that means you need higher barriers to allow you to do that, along with a moderate increase in effective mass. So I believe, but I'm not 100% certain, that the right solution for the next generation, in fact, is an indium phosphide channel, bit higher effective mass. And then you would want something like an antimonide, gallium arsenide, antimonide, excuse me, aluminum arsenide, antimonide back barrier, so it's high enough that you can raise the Fermi level. So I believe that's true, but I don't want to state it with absolute confidence because I'm not fully confident in the correctness of my ballistic transport calculations. Yeah, but unfortunately, that's a really major change in the semiconductor technology. So again, there's got to be a big driver in terms of potential market impact, whether civilian or military, to want to do such a thing.
Mark,
Yeah.
can I ask a question?
Yeah.
You have told me, and I have heard from many, that a lot of these ideas and a lot of these structures that you are showing are already used in the CMOS industry when they go down to 14 and 12 and 7 nanometer, and then that the channel is really not silicon anymore. It has SiC in it, and it has
silicon.
It has everything in it.
I've lost track, but I'm forgetting, and others in the audience probably know, so let me not speculate. But in some cases, there's significant silicon germanium in the channel. Yes. Yeah.
But I also hear that there might be also some 3-5 things in the channel too.
I don't know. I can't say. You may know more than I do on that.
I doubt that.
Yeah, I doubt it. I doubt it.
Okay.
But yeah.
But germanium definitely, some SiGe definitely. And
Yeah,
hence
and the
structure.
strain engineering and there's orientation engineering and further quantum confinement. There are a whole bunch of things being used to engineer and change the silicon band structure in modern nanometer 3.5 MOSFET so that the EK dispersion looks nothing like your textbook. Yeah. Yeah. But having said that, the carrier velocities are considerably lower than the in-gas channel field effect transistors. You see this in the RF data, right? Yeah. So it's a good question. Unfortunately, in this format, your question has so many variables in it that it's hard to properly address your question in this venue with such limited time.
But also with very short channels, you're not really dealing with velocities. You're dealing more with ballistic transport too. And
yeah. So in the case of the in-gas field effect transistors, our data suggests that the currents we measure are on the order of like 80 to 90% of the ballistic limit. In the terms of silicon field effect transistors, I don't have that data, and I eagerly refer to all of Mark Lundstrom's papers. But I don't have I mean, certainly drift diffusion doesn't work, but what percentage of the ballistic limit it is in a modern silicon transistor, I don't immediately have a sense of that. But it isn't as high as but I guess the point you would make, which is certainly correct, is, and this is Mark Lundstrom, Dimitri Antionadis, and others, there's a huge body of ballistic and semi-ballistic transport analysis of modern silicon VLSI, and it's a part of the understanding of these devices. And of course, there's a tremendous amount of ballistic and semi-ballistic modeling by people like Gerhard Klimek at Purdue, right? Who work to understand these things in great detail. The 3.5s is easier because the scattering rates are such that you're much closer to that ballistic limit in the small devices. Yeah. I guess I would comment that the current gain cutoff frequencies being so high in the indium phosphide HBTs is that not in the full collector thickness, but over a range of bias voltages, you're getting a good half of the way through the collector before the electron scattering. So there's a region of ballistic transport in there. And that has a lot to do with why the cutoff frequencies are so high. Yeah.
yeah.
Okay.
But wait. Remind me one thing.
Yeah.
Ballistic speed is independent of drift and drift diffusion speed, completely independent.
Yeah, the different phenomena, but it has to do with the energy relative to the conduction band, and the mass is often anisotropic, and it depends on the mass and the direction of transport.
Yeah, because I think silicon has a higher ballistic speed than gallium arsenide for pin diodes and things like that.
No. Well, again, it depends on the voltage, but because the effective masses are lower, the ballistic velocities are higher in most of the compound semiconductors. But you've got fewer quantum states to work with because of the higher mass, and so there's this trade-off which Peter explored in his question to much greater length. Yeah.
One more question in the chat room, if this interesting discussion is paused. The next question is from Robert. Great talk. Any thoughts or insights on how the low frequency noise will be impacted / improved at these advanced nodes?
So low frequency noise, I'm not an expert on, so I say with a degree of speculative abandonment that it has to do with population and removal of charge from traps generally at the surface. So that tells you that field effect transistors have more 1/f noise than bipolar transistors, and we know that. It tells you that silicon with a lower state density at the surface has lower 1/f noise than compound semiconductor devices. And it also tells you that as you more highly scale a bipolar transistor, because you're making the lateral dimensions narrower, there's more the ratio of surface to volume again is getting bigger. And so the more highly scaled high frequency devices, you would expect to have more 1/f noise. But just with the scale of the efforts at UCSB or Teledyne, no one has the resources to measure that. I would comment again that if you do it right with base regrowth, as you know, presuming that you do it right and don't have defects buried in the structure, regrowth is a great way of avoiding the degradation in 1/f noise with scaling. And I should comment that our base regrowth efforts have been aimed at higher fmax, but you can also use the regrowth to get higher DC current gain, and that helps not with ultra low frequency 1/f noise, but the midband noise in frequency independent noise. So again, base regrowth in the indium phosphide HBT would give it scaling properties similar to the SiGe HBT, where you wouldn't see that degradation, slow degradation in 1/f noise as you make faster transistors. Yeah.
Well, Mark, you hit on something that's close to my heart due to FMCW or different radars. We have measured the 1/f noise for different SiGe transistors in different processes, and they vary by 10 dB.
Interesting.
I mean,
well, so again,
approximately the same, within approximately the same, maybe 4 dB, 6 dB, but within approximately the same node. I'm not comparing a 0.35 node to a 0.13 node. I'm comparing like the best node to the best node, and we see a variation in the 1/f noise.
So again, I'm not an expert, so I'm just speculating on what I see in the literature. But although the SiGe HBT has base regrowth and often also emitter regrowth, the regrowth is often polycrystalline. And then there's often a recrystallization step, but it leads to the obvious question about how far do you have to get away from the junction before you're starting to see defects. And so again, just wildly speculating with no first-hand knowledge that maybe what you're seeing is different degrees of distance from the crystalline p-n junctions and the amorphous polycrystalline regions. The not amorphous, the polycrystalline regions, which will have some defects. So yeah.
Which basically what you're saying, it's only a fabrication tweak, like temperature and relaxation tweak, and that's it.
I would think so, yes. Yeah. Yeah.
Maybe time for one more quick question, if somebody has one. Otherwise, I can close this out with the 2 slides that Amy has put up for me to talk about. I'll pause for just a second to see if we get one more question.
Shall I stop share?
Amy has already done that for you. She took over the screen. Thank you, Mark.
Okay.
But I will say thank you, Mark, for the great seminar and for allowing time for that valuable discussion, and for all of the participants who asked questions and participated in the discussion. That was really insightful and great to be able to listen to. As we wrap up here, I will just say, please scan the QR code for information on the technical seminar. And remember that we have a YouTube channel for the archive talks that you've missed live. When you go to YouTube, please click like and subscribe so that our channel can become more publicized and more people can see this good content. And please tune in upcoming weeks where we have interesting talks coming from Shia Feynman, Jonathan Klampkin, Hamid Reza Agassi, Steve Zamek, and others coming soon. So thank you, everybody. Thanks again, Mark.